Welcome to this explainer. You know, when you really think about it, everything we can actually see out there, the stars, the planets, you and me, it all makes up just a tiny, tiny fraction of the universe. The rest, well, it's tied up in the ultimate cosmic missing persons case, dark matter. Today we're going to untangle a totally fascinating web of astrophysics and cutting-edge particle physics. What I absolutely love about this research is that we're diving into a brand new investigation, one that relies on a very special type of cosmic messenger to hunt down this missing mass. Okay, let's just dive right in.
We're going to start by plunging straight into the core of this mystery. For decades now, scientists have known that most of the matter in our universe is completely invisible. We call it dark matter, mostly because it literally holds our galaxy together, but we still don't actually know what it is. But what if it's not some new, undiscovered particle? What if the universe's missing mass is actually hiding inside incredibly ancient, completely microscopic black holes?
To ground this in some very recent scientific drama, we really need to look at a crazy event from February 2025. The researchers point out that the KM3 NET telescope, which is this massive underwater detector, caught an unexplainable, extraordinarily high-energy neutrino at 220 peta-electron volts. That stands for peta-electron volts, and it is an absolutely massive amount of energy. It sparked immediate wildcard theories all across the astrophysics community. The tension with other telescope data made it super unlikely to just be a standard flash from a typical cosmic event. Instead, it raised a truly thrilling question. Could this extreme particle have literally been shot out of an exploding microscopic black hole?
To answer that, let's officially meet our primary suspect in this missing mass case.
Our suspect is the primordial black hole, or PBH for short. And what's absolutely crucial to understand here is the distinction being made. These are not the massive black holes formed by dying stars that you usually hear about. No, primordial black holes are theoretical objects born from the collapse of incredibly dense pockets of matter in those chaotic, microscopic fractions of a second right after the Big Bang. They are literal ancient relics of the early universe.
So what do these ancient relics actually look like? Well, specifically, scientists are hunting in what's known as the asteroid mass gap. They're looking for primordial black holes that weigh up to about 10 to the 17th grams. To put that into perspective for a second, they have the mass of a literal asteroid, but physically, they are microscopic. We're talking smaller than a single atom.
Which of course brings us to a massive logistical problem. How on earth do you find something so impossibly small and totally dark?
You look for the leaks. As Stephen Hawking famously theorized, black holes aren't actually completely black. They evaporate due to quantum effects, emitting what we call Hawking radiation. And this brilliantly illustrates a really bizarre, almost counterintuitive quirk of physics called the inverse mass-temperature relation. Think of it kind of like a boiling pot of water. The smaller the black hole is, the hotter it gets. And the incredibly surprising part is that the hotter it gets, the more violently it emits particles, right up until it eventually just explodes.
And this violent, super hot evaporation at the microscopic scale brings us perfectly to our newest forensic tool.
To find these evaporating suspects, scientists are turning to high-energy neutrinos. But why neutrinos, right? Why are they the perfect tool for this specific job? Well, they act as the ultimate cosmic messengers. They're often called ghost particles because they carry zero electrical charge and have almost zero mass. This means they just zip through almost everything. Stars, entire planets, massive magnetic fields, completely unhindered. They're emitted directly during this Hawking evaporation, which gives us a pristine, totally unfiltered look across vast cosmological distances, straight back to the source.
But as you can imagine, catching a ghost particle requires a pretty serious trap. To do this, scientists use these massive neutrino telescopes buried deep in the ice and water of our planet to act as giant cosmic magnifying glasses. Looking at the baseline data, we rely heavily on current telescopes like IceCube down at the South Pole and Antares in the Mediterranean. But the future is looking really bright here. Upcoming telescopes like IceCube Gen 2 and the fully realized KM3 NET will offer massive sensitivity improvements, essentially turning up our ability to catch these particles by up to a factor of 3.5.
Now, with these massive telescopes in place, the researchers in our source material outline two very distinct ways to hunt for these suspects.
We can either look for what's called the diffuse neutrino flux, or we can attempt to spot a singular transit. The diffuse flux is essentially the combined background glow of billions of evaporating primordial black holes scattered everywhere throughout the universe. A singular transit, on the other hand, is exactly what it sounds like. We try to catch the specific neutrino emissions of one single primordial black hole flying right past our local cosmic neighborhood.
Let's look at the singular transit first, because it has a major problem. It really comes down to sheer probability. For our current high-energy neutrino telescopes to achieve a rigorous 5 sigma statistical detection, which, by the way, is the gold standard of absolute certainty in physics, a single primordial black hole traveling at a typical dark matter velocity of roughly 200 kilometers per second would have to pass within a tiny fraction of a parsec of Earth. In cosmic terms, that is basically shaving our atmosphere. Even with our massive telescope arrays, the chances of a microscopic black hole flying that incredibly close to us during our observation window is just, well, exceedingly unlikely.
So, because of that, the crucial point the researchers highlight is that the most reliable forensic evidence actually comes from the diffuse flux. By looking at the all-sky background, researchers can combine the neutrino emissions from primordial black holes gathered in the really dense galactic ridge of our Milky Way, the wider galactic plane, and even those from vast extragalactic distances. Think of it as listening to the faint hum of the entire universe, rather than just waiting around for a single isolated shout.
All right, so after compiling over a decade of this high-energy neutrino data, mapping out their diffuse flux, what is the actual verdict?
The researchers arrived at a very compelling, albeit conservative, conclusion. Based purely on the diffuse high-energy neutrino data we currently have, primordial black holes lighter than roughly 3 times 10 to the 17th grams absolutely cannot make up 100% of the universe's dark matter. The neutrino glow we would expect to see if they were everywhere in that specific mass range just isn't there in the data. So they might definitely be part of the solution, but they aren't the whole enchilada.
But don't worry, this case is far from closed. While current data constrains the very bottom of that asteroid mass gap, next-generation telescopes are going to push those constraints much higher, up to 2 times 10 to the 18th grams. And here's a super fascinating twist. What if these primordial black holes aren't static? What if they're actually spinning, what physicists call Kerr black holes? The physics of that spin would actually cause them to evaporate much more aggressively. If they are spinning, our detection bounds immediately improve by a factor of 7. No joke, a factor of 7. As the authors of the study beautifully summarize, the next generation of neutrino detectors is going to drastically narrow down the hiding spots for dark matter. When they talk about ruling out that mathematical term, FESPBH equals 1, they basically mean ruling out the possibility that these tiny black holes make up 100% of dark matter at those higher mass ranges. By probing deeper and deeper into this asteroid mass gap, we are systematically cornering our suspect, using these ghost particles as a completely independent cosmic probe.
Which leaves us with one final, totally thrilling question to ponder as we wrap up this explainer. With that crazy 220 PeV event from KM3net already hinting at some unknown astrophysical extremes out there, are we teetering on the brink of finally catching one of these microscopic black holes in the act of exploding? Or, as our telescopes grow ever more powerful, will we soon close the book on them entirely, forcing us to find a brand new suspect for the universe's missing mass? I really hope this journey helped clarify this incredible ongoing hunt for you. Until next time, keep questioning the cosmos.